All right, welcome to our presentation for Module 5, where we'll look at numerical methods for differential equations. So still looking at just first-order differential equations, we'll just look at the Euler's method and then methods that came from that. And we'll start with Euler's method, and we'll look at a specific example. So we've got a first-order initial value problem here, y prime equals 2 plus xy. And then our initial condition y of 0 equals 3. And you notice that not only do we know the value of the solution at this one point, we can use those coordinates to find the value of the derivative at that point, and thus we know the slope of the tangent line at that point. Now, if we go to a graph, knowing that point and the slope, which is 2, by the way, having a line of slope 2 there, that really doesn't tell us for sure what the solution is. Because we could have multiple curves go through that point and have that derivative of 2 at that point. And so our solution could do any one of these things, right, in the long term. But if we zoom in close enough, what we'll find is no matter what the solution is doing far away, close by, it is essentially acting like this straight line. And that's the idea behind Euler's method is if we take a very small movement in the x direction, the y change should be about the same as the straight line given by the tangent line at that point. All right, so let's now move along a little bit along that straight line and look at this relationship. If we chose delta x to be 0.1, and in general we get to choose delta x, 0.1 is pretty big, but we want to kind of exaggerate it. We can make that smaller to make this more accurate later. And then we see the corresponding change in delta y here. And in general, that's what we want to figure out. So we'll choose the change in x, and then we want the method to calculate how y changes. And so you want to remember that the slope, which is the derivative, is change in y over change in x. And if you just multiply that by delta x, then you get delta x times y prime equals delta y. So we can find the change in y by taking this change in x, which will become sort of our step size, and multiplying by the value of the derivative, which comes from the differential equation. And so you could see if I had a derivative of 2, and then I had a change in x of 0.1, multiplying those, I get the change in y is 0.2. And I can use that to tell that y increased from 3 to 3.2. Right? Remember, y was initially at 3, and so now it's going to be 3.2. So that's how Euler's method will work. But before we go on with that, just make sure you can practice finding the change in y for a different problem. So I've got you an example here where you can use this differential equation and initial condition and that change in x to find the change in y. All right, pause it if you need some more time, but remember that the change in y is equal to the change in x times the derivative. And our change in x is 0.05. And for our derivative, we would use these values that x equals 0, y equals -3, and we would put that in the differential equation. and see that the derivative is -3. So the change in y is the change in x 0.05 times the derivative -3, or -0.105, which is a. Now, in general, we always want to kind of put our differential equations in this format, and then this is often referred to as the function f. So solving for y prime or dy dx, then the other side is this function f, which is a function of x and y. And you'll use that to calculate your derivative. So if you see f, that's the same as y prime or dy dx. Right, back to our problem. So here I've taken one step with Euler's method, and just to recap, I had my my differential equation y prime equals 2 plus xy, my initial condition 0, 3. So starting at 0, 3, and then I get to pick this step size, delta x, though in a lot of the formulas in code, it'll often be denoted with an h. And I chose 0.1. We know that's a little big, but we get to make that smaller if we want. And then the subscripts tell you the different discrete values of the solution. So we'll usually let the initial conditions be x0, y0, or x naught, y naught. And so the first x value is that initial value of 0, and the first y value is that value of 3. So that's our x naught and y naught. And to get the new x value, I just take the old x value and add on the change in x, or h, or step size. So 0 plus 0.1 equals 0.1. So my new x value is 0.1 because I moved from 0 to 0.1. Now for the y value, I need to take the old y value, y naught, and I need to add the change in y. So using our notation, delta x is now h, and then the derivative is y prime is evaluated at x naught, y naught. So we take those initial conditions of 0 and 3, we put them in the differential equation, and that gave us a derivative of 2. So 3, my initial y value, plus change in x, 0.1 times derivative 2, and I get 3.2 for my new y. Now, in general, the solution itself is nonlinear, and so it's going to have a curve to it. So the tangent line is never going to be exactly matching up with it. And this leads to some error between the approximation from the tangent line and the actual solution itself. Now, if we take multiple steps, we will see that we get further away from the actual solution. Again, these are sort of exaggerated errors here. But in general, we'll always get the new x value by just adding the step size to the previous x value. And we'll get the new y value by adding the change in y to the previous y value. And that's always the step size h times the value of the derivative, where we keep evaluating it at the previous x and y. Now here we see taking 4 steps with Euler's method and the accumulation of the error. Now we can control the error a little bit with the choice of step size. The graph here shows the solution, exact solution in green, and our largest step size in pink of 0.2. If we cut that in half to 0.1, we get closer. And then if we cut that in by 1/10 to 0.01, we get almost indistinguishable from the solution. So that's one thing we can do, is just decrease the step size to decrease the error. So we can improve upon Euler's method and get the so-called improved Euler's method by doing the following. Here is our solution and our initial condition at A, and using Euler's method, we can calculate the derivative or slope of the tangent line at A. And then if we move along that, this would give us our Euler's first step. But rather than using that as a stopping point, we recalculate the slope there. And notice that the slope at A is pretty steep and the slope at B has gotten smaller. And then we can average those two slopes. And by doing that, we will know that second derivative is negative and that the actual slope is decreasing. So calculate the slope at A, take one step with Euler's, recalculate the slope, then average those two slopes, and then that's the slope you move along, getting us to point C, which is a much better approximation than Euler's would be at B. That's the idea behind improved Euler's. And looking at the pseudocode, the x's part is the same. We just add our step size to x. But we introduce these two slope calculations, and we use K1 and K2 to denote the two slope calculations. Again, F here is just the right side of the differential equation equal to the derivative at that point. And so K1 is just the Euler's slope calculation, the initial one. So the slope of that one, that's your K1. And then if we take a step forward with Euler's and get your new y value, we recalculate the slope, that's K2, the slope of that line. And then we average those two together, add them up and divide by 2, and we use that slope to move along. So that's K1 plus K2 over 2, moving along there. And then we still use that slope times the change in x to get the change in y. So this gives us a much improved result with Euler's method. And one step really involves two kind of function evaluations of the derivative. And then obviously people thought of extending this process to take more approximations of the slope and average them in more clever ways. So this leads to a whole family of methods, and really the pinnacle of all that is this Runge-Kutta fourth order method, at least for sort of an introductory approach. And with the Runge-Kutta method, we still start off with an Euler's method first step, except we only take a half step. So K1 is the Euler's method slope. Take a half step with that, recalculate the slope there. That gives us K2. Go back to the beginning, move a half step with K2, recalculate, get K3, go back to the beginning. Now take a whole step with K3, recalculate the slope, get K4 at the end, and then average the 4 K values. Now, not adding them up all and dividing by 4, but actually you add up, put a double weight on K2 and 3 since they're in the middle, and then you add up those 6 slopes and divide by 6. So it's a weighted average, putting a double weight on K2 and K3 since they are in the middle. So you can see the pseudocode here, x is the same as the other methods, but now we have 4 K values. Each one is the valuation of the differential equation to get the slope. The first one's still Euler's method, then using half steps twice in a row to get K2 and 3, and then a full step to get K4, and then averaging all those up and multiplying by the step size to get the new y value. So yeah, this is the Runge-Kutta 4 method. There are other Runge-Kuttas that involve 5 steps and things like that, but this won't be looking at in this class. So obviously these are designed to be done computationally, and we'll look at doing this with Python, but you could do this with any computer programming language. And we'll be able to look at error analysis and approximating solutions in the methodologies. There's a methodology for each of these 3 methods. Before we wrap up, again, this presentation contains images and text from the Elementary Differential Equations and Boundary Value Problems by William Trench, which is CC BY and CSA. See you in the methodologies for this module or in the next presentation video.